In this example, we're going to continue to use the LOL chart to solve a conservation of energy problem. A vernier cart with a mass of 1.0 kilograms is launched by a spring which was compressed by 3.6 centimeters. The cart rolls up a ramp to a height above starting position of 2.0 centimeters. Determine the spring constant for the spring in the cart. Again, let's define our system. It's going to include the cart and the spring in the cart. We could add that just to specify it. It's going to include the ramp. And then something else I forgot to add on the last ones where we've dealt with UG. Anytime you deal with gravitational potential energy, you should include planet Earth because the gravitational potential energy comes from Earth's gravity. So that just really makes it proper the way that we're including Earth in terms of gravitational potential energy. Well, this cart starts with all elastic potential energy. So I'll give my bars to elastic potential energy there. And then by the time it gets to the top of the hill, top of the ramp, it's got UG. Now, there's no work going in or out of the system in this case because I'm including the spring as part of my system. So I don't need to have that as an outside different system. Alright, so this makes it pretty straightforward for this one. We've got US initially equals UG finally. Then we will define each of these. Elastic potential energy is 1/2 times K, the spring constant, times delta X squared. And UG is mg delta Y. We're trying to solve this one for K, so we could go ahead and rearrange and solve this for K in terms of K. Multiply both sides times 2 to get rid of the half. And then divide by delta X squared. And then we've got this nice neat equation ready to solve for K. mg delta Y, or 2mg delta Y, all over delta X squared. And then just to make some space, I'm going to make some little rectangles up here so I can continue this problem up above since I'm out of space. Alright, so I'm going to solve for K. K equals 2 times the mass of the cart, which is 1 kilogram, times 9.8 meters per second squared, times the height in meters, so we'll stick with joules here, 2.0, or 0.02 I should say, meters, all over 0.036 squared. Alright, so 2 times 9.8 times 0.02. I've got 0.392 on top. Divided by 0.036 squared is 0.001296. And I'll work it out. 0.392 over 0.001296. Looks like it's about 300 newtons per meter, because that's our unit for the spring constant, about 302 newtons per meter. And we solve for the spring constant using conservation of energy and the energy bar charts.